Good morning, good afternoon, good evening, wherever you are. Thanks for joining us today for today's webinar. As Blake introduced, my name is Joe Xavier. I'm the Regional Technical Manager for ABB's Distribution, Protection, and Automation business. For the West region, I'm based out of Southern Washington State, close to Portland, Oregon. And I'm glad to be your presenter today. So let's get rolling here. So today's objectives of the webinar is three. Number one, we will look at what is the digital switchgear very briefly, and then talk about the selection of protection within digital switchgear. And thirdly, we will also briefly touch upon some of the applications, how the different protection relays can be applied for different applications. Okay, so some of you may be familiar with the digital switchgear. What is really digital switchgear? So if you can look at a traditional switchgear or a substation environment, you would see a lot of copper wires. Okay, so on the screen here, you see a picture with a traditional substation environment with a lot of wiring going around. Okay, so here you see a cable tray running, which carries all the cable because each panel requires multiple cables with respect to wiring of CTs, PTs, and also wiring the inputs and outputs from the digital or the relays itself, and also wiring between the panels. So you have some protection scheme, interlocking scheme, ATS scheme, and so on happening or designed to work between the panels, between the relays of different panels. All those things have to be wired together. So there is a ton of wires drawn through different panels, and there's a dedicated cable tray, as I mentioned before. And digital switchgear is one of the pictures here on the right. There are no cable trays, just a single conduit to carry fiber optic cables. So that's all we're talking about. It becomes a very neat execution, and obviously there are many other benefits we will go through one by one in the upcoming slides. So one of the main drivers for digitization is to replace the copper or eliminate the usage of copper in the panel. And of course, there are other associated risks with respect to the operation and maintenance of a traditional panel. When you have more wires, you require more maintenance, and also it adds to the risk associated with the safety and so on for the people who are operating the gear. And in many cases, or one of the common reasons, you have some issues within the panels are due to loose connection many times. So loose connection between the wires, copper wires. So many such associated things, and we are trying to make a better, simpler construction and design with the digital switchgear and make it more safer and more efficient with respect to operations. Okay, so how do we replace the copper wiring? And as I mentioned earlier, the copper wiring is primarily from the CT and the PTs, which are installed in the panel, and also between the IOs of the relays, inputs and outputs of the relays, and also between the panels, between the relays, to make a protection and control scheme. Now, to replace the wire, to replace the copper wiring, the technology what we have today is based on IEC 61850 standard. Some of you may be familiar with 61850, but if you are not, and if you're wondering what is IEC 61850, it is an open global standard for power system application. So The name IEC, of course, says that it is IEC, but if you really look at the genesis of the standard, it comes from both worlds of ANSI and IEC together. The ANSI world has a UCA standard, and IEC had a similar standard, and at some point, both the standard groups started working together and formulated the standard called as IEC 61850. And the IEC 61850 defines all objects in your electrical one line. So it's a data modeling standard for power system application. And also it provides interoperability between different vendors. What that means is if you have multiple vendors, devices, protection and control IEDs in your system, they will be able to talk to each other. You can make protection control and communication scheme between those if everything complies with IEC 61850 standard. So in that, and that is one of the main drivers for this IEC 61850 standard. And so IEC 61850 is a very broad standard, and a big part of it is communication. And the different aspects of communication which enables digitization of the switchgear are mentioned here in the second half here. One of them is called as IEC 61850 MMS. It is a manufacturing messaging specification which facilitates vertical communication. So typically master-slave component part of the communication where the devices talk to the upper level communication, a gateway or a SCADA and so on. And then the other part of it is called as goose messaging. Goose messaging in IEC 61850 is a peer-to-peer functionality where different devices can talk to each other. Multiple devices can talk to each other. And this goose message is fast. As per the standard, for the distribution, protection and control application, the goose message is guaranteed time is less than 10 milliseconds. And the third aspect of 61850 communication is sample value sharing. And it's also called as a process bus, where the digitized current and voltage signals between protection relays are shared between the relays, between the IEDs. And the receiving IED can use that current or voltage signal for protection, measurement, and recording functions and so on. Whatever a relay can do with a directly connected CT or a PT signal, the same functionalities can be achieved by subscribing to the sample values. That is a digitized current and voltage signals. So this is a big enabler for making a digital switchgear. Okay, so what is the minimum requirement for a digital switchgear? Obviously, as we discussed, the protective relays, so the IEDs, should support IEC 61850 standard completely. It should support 61850 edition 2. It should support IEC 61850 8-1, which is the station bus standard, which involves a vertical communication, MMS, which we mentioned, and also the goose communication, which is a horizontal communication. And it should also support 61850-9-2 LE process bus, or the sample values, as we mentioned. So that's the standard which governs the sample value publishing and subscription. And the other minimum requirement is the input availability for low energy analog inputs, popularly known as LEA input, that is a low energy analog input. I will mention about that in a second. So what is a low energy analog input? So these low energy analog devices are the devices popularly known as sensors. So you have the picture of sensors here. So these sensors are used to replace the traditional CT and the PT. So here is the picture of a current sensor. It's based on a Rogowski coil principle, and this current sensor brings out a millivolt signal on this Ethernet cable here. And this this guy will replace a traditional CT. And down below here, what you see is a voltage sensor. It's basically a voltage divider. And this device, this voltage sensor, as we call it, replaces the traditional PT in a switchgear. So these are the low energy analog output devices. So the output of these devices are millivolt or volt signal, which gets which goes into an adapter. So this is this is per phase. What you see here, let's say it's an A phase current sensor and the voltage sensor, and then it gets through an adapter. The signals are combined and is fed into the IED. So here, what you see here is an test switch called as FT14D. It's a digital test switch from the same family of FT switches popular in North America. So we have a digital version of it, which can take the sensor input, and then the output of that goes to the IED. So from the relay standpoint, the relay has 3 inputs, 3 RJ45 type input, which that is 1 per phase. So 3 inputs goes into the relay, where the current and voltage from each phase are clubbed together and fed into the device. So if you look at a relay with the current sensor input, you will not see the traditional CT and the PT terminal blocks. Instead of that, what you will have is 3 RJ45 type input. Now, associated with this FT14D, there's a digital switch. You have a test plug available as well. So this is basically for ease of testing purpose. So if you're future testing, this can be used along with a test plug, where any standard secondary injection test kit, which is capable of injecting LEA output, can be used to inject the LEA output into the relay, bypassing the sensors. So that is the arrangement here. So this is very similar to the traditional CT-PT wiring and using an FT switch, but in this case is an FT14D switch. Okay, so this is one aspect of digitizing the switchgear. Okay, so what is the other aspect of digitizing? So from the previous slide, we saw about the sensors, the current and voltage sensor. So here in this one line, I want to spend a minute here to explain what this one line is. Here is a main lineup with multiple outgoing feeders. So here is main 1, and there is a tie breaker, and there is a main 2. Now, if you look at the main 1 here, this symbol, what you see here, is for current sensor. So this is the current sensor feeding the current from main 1 into its relay, its IED. And the voltage sensor, this is the voltage sensor, is feeding the voltage into this IED. Okay, so similarly the same setup is for the main 2 as well. And so these 2 main relays have the line PTs, or sorry, I should not say PTs, it's a sensor, the line sensor, voltage sensor connected to it. So it has a line voltage on the main relays. Now, from the bus voltage standpoint, on the bus A, you have a voltage sensor, which is connected to this feeder relay here. Okay, so this is the bus voltage sensor. And its respective current sensor is connected to the relay as well. But whereas the other relays on this bus A need not have the direct connection of the voltage sensor to the other relays. But how will it get the voltage signal? So that is sent over the sample value. So this bus voltage from relay A is sent over as a sample value message, and the other relay subscribes to that. So that is what is how the voltage sharing is achieved. Now, with respect to the bus B, there is a bus B voltage sensor as well, which is mounted in the tie breaker here in this case. So the tiebreaker relay has the bus voltage input as well. Okay, so, and that voltage is shared between the relays on the bus B. So there is no wiring required between multiple relays from the same voltage sensor, or in the traditional sense from the same PT. So we are using that sample value sharing here. And each panel has its own respective current sensor. And another facility here is also with respect to sync check application. So when you have multiple sources to be connected together, we always need to be checking the synchronizing condition. So in this case, the tiebreaker, if you talk about the tiebreaker has the bus B voltage directly connected to it, but it can subscribe the bus A voltage over the sample value from here. And then that information is used for check sync application. So it uses the check sync application, one from the directly wired voltage, other from the sample value. So this is how, you know, the sensors in conjunction with sample value sharing makes the panel design much efficient. And in addition, then we have goose messages as we see here. So the goose messages are nothing but the binary input-output signals, which are to be transmitted to multiple relays, especially with respect to interlocking schemes or protection and control schemes like fast bus protection, zone selective interlocking, or circuit breaker failure protection, or anything of that kind of application can be achieved using the goose message sharing, where one relay can send its status, strip status, pickup status, or IO status to other relays, and it will subscribe those signals and take action based upon that. So we totally eliminate inter-panel wiring by using goose messages. And then I should also mention that in this example, in this case here, so these relays double up as merging unit. I would like to mention about a merging unit. Merging unit is a standard industry name for the device which digitizes the current and voltage signal in a protection system. So in this case, this device is a protection relay. At the same time, it also acts as a merging unit, which means it converts this signal, the voltage signal, and publishes out as a sample value. So the relay doubles up as a merging unit. So it makes a very, very efficient design. Now, we talked about many things with communicating signals over for the IO status as well as the current and voltage signals shared between the device, which means we need to have a very robust communication network. So that means to say that we need to have a redundant communication network to make sure that nothing is lost at any point of time. So there are two popular redundant solutions supported by IEC 61850. One is called as PRP, and the other one is called as HSR. PRP is a parallel redundancy protocol where each network is connected to two parallel local area networks, a LAN A and a LAN B. So if you note here, each device is connected to two different networks. Every device is connected to two different networks. So it's basically duplication of the network. So everything is duplicated. The same data is sent on both local area networks. Okay. So with this arrangement, we are sure that no data is lost at any point in time. So if there is a problem in one network, the other network is 100% active. So, and when if there is a problem in one of the networks and the other relays are not receiving duplicate messages, that means there is a problem in one of the networks. So that's how the device is also identified if there is a problem in the network, it alarms. So there is a provision to alarm that. So whereas in the case of HSR, it is a high availability seamless redundancy protocol, as we call it, and that is a ring topology. So again, the same, each device will have two ports, and the nodes are connected via 2 ports to the network. So that means these communication ports are networked in a ring form, and the data from each device is sent in both directions. The same data is sent in both directions. Okay, so again here, there is no, the failover time is totally eliminated. If there is a network problem in one path, the data it comes back to the healthy section of the network, and the process is taken care. Again here, because the relay will not see the duplicate messages, so that means the relay identifies that there is a network problem as well. But again, there is no data lost in both HSR and PRP, so there is zero downtime. Okay, so with respect to traditional and what is the benefit, real benefits achieved by digital switchgear, it of course reduces the footprint because we are probably eliminating a PT compartment in a switchgear, because the sensors are very compact, very small devices, and overall footprint of the switchgear can be reduced, and it eliminates a lot of copper wiring. It improves the safety of the equipment because we are not dealing with the open CT conditions anymore by using sensor, and there are no higher voltages and currents like 120 volts or 5 ampere to be dealt with when we are using sensor. And also we are also eliminating the CT saturation condition, because the sensors are linear devices, which means there is no saturation in that. It offers a very wide range of current for its operation, which enhances the reliability of operation, and it reduces the overall cost of ownership. Okay, now switching gears a little bit, looking at the protection, how to select protection for a digital application. So just going to the fundamentals of protection, the protection relay is selected based on the zone of protection, or the zone it has to be protected. So there are 6 categories of protection zone in power system. As you can see here, it can be, the one is a generator and a generator transformer unit zone. Then there are transformers in the power system, so we need to protect that. And then there are the bus bars, so we need to protect that. And there are transmission lines in the power system. It could be at the transmission level, sub-transmission level, and at the distribution level. So we need to protect that part. And also the zones are categorized based on the utilization equipment. For example, motors. So if there's a motor that's a load, and that's a equipment to be protected. And also the other category is a capacitor or a reactor bank where separate protection is needed. So this is how the power system is broadly categorized. Excuse me. So here is an overall view of the different devices and the solutions we can offer for digitizing the switchgear all the way from sub-transmission level into the distribution level, and of course to the low voltage network. So we have different control and protection control devices, standalone devices, and also all-in-one devices. I have more details in the upcoming slide. So in addition, there are system level applications like SSC 600 and COM 600 or Xenon, which is a substation gateway, substation automation solution, which all works together to make digital switchgear a digital substation. And Also, there are some communication devices in the portfolio. So this is just an overall view of what electrification digital solution can offer to make a digital switchgear. Okay, now getting into the finer details of the product itself. What goes into the digital switchgear, or this is beyond that. This is an overall view of the different IEDs which are used. So in Reliant Protection and Control, that is ABB's protection and control platform, which is used globally. We have different series of products under Reliant. What you see here is a Reliant 605 series, which is the most compact protection and control device. And then we have a Reliant 615 series, which is a box which has a lot of flexibility and functionality, and also Reliant 620 series. The Reliant 620 series is for high-end distribution application and has a recloser control application, and also Reliant 640 and SSC 600. So I have more slides on 640 and the SSC. So to mention a few things about 615 series. So here is this is one of the popular series of ABB being used globally, and 615 series products, and for that matter, any product under Reliant is named the common naming structure is RE, stands for relay, and the third letter will tell you the application. For example, REF means it's a feeder protection relay, F for feeder. So REF 615 belongs to a 615 series relay. RET 615 is a transformer relay. REM is a motor relay. REG is a generator relay, and so on. So that's how the products are categorized. So these are application-specific products, which means an REF is dedicated for feeder application, REG is dedicated for generator application, and so on. When it comes to 640, it's a different concept. We call it as an all-in-one protection relay. So it is a comprehensive, it has a set of base functionality and an optional application package. So what you see here, you can have a base package always, and on top of it, you can have optional packages like this: a feeder, extended feeder, transformer, machine, shunt reactor, or shunt capacitor, synchronization, and so on. So there are different application packages you can choose from on top of the base package. Okay, and several application packages can be combined to meet specific power system protection requirement. And all these applications can be covered with functionality in one device, which means you save time and space configuring different devices. So it covers a full range of utility and industrial application, and it is easy to select and conveniently specify for any need. Okay, so this is the concept of REX 640. So here is a little more detailed view of the different application packages REX 640 can have. For example, base functionality covers all the basic overcurrent ground fault protection like 50, 51, P and N, and so on, restricted earth fault, voltage protection, frequency, and load shedding. So in addition, if any of the other protection applications are required, we can load these additional protection applications on top of the base functionality. Okay, so I need to mention that we can, some of the commonly used one are the power transformer protection, machine protection, interconnection protection for connecting distributed generating units. Then there is a shunt capacitor protection. Then there's a bus bar protection, which has a high impedance based bus bar protection scheme, and also an extended feeder or line protection, including fault location, line distance protection, line differential protection, and so on. So if there is any application covering that, we choose this package. And there's a tap change controller, generator synchronization, and network breaker synchronization. Peterson coil control. This is a very unique feature we have for controlling the Peterson coil for high impedance network, mostly utility application. And also we have a package for arc protection. Okay, so the next the product we have is the SSC 600, which is a smart substation control and protection. It is otherwise known as a centralized protection and control. It's a brand new way of substation protection and control, where it incorporates a centralized protection, control, and monitoring functionality, which means you have one device which can protect up to 20 bays, or 20 feeders. So you have one device, and then it also works on IEC 61850, which we talked earlier, which subscribes the sample values from its respective feeder, and also can use goose messages to do the interlocking, and also the signal sharing between the devices. It's designed for a wide range of power distribution protection application, starting from basic feeder protection and to complex multi-feeder substation application. And it delivers the flexibility, so that it adds to the flexibility and to modify or for the changing network. So the networks are constantly changing and evolving depending on what comes into the network and future expansions and so on. So there's a great amount of flexibility in modification for future needs with SSC 600. And it enables visibility to view and monitor process at the substation level from the centralized point. For example, disturbance records. So that is one of the benefits here. You can view the whole substation status at one point. All the disturbance records from all the different feeders are available at same place. So that is a very nice and useful feature with respect to the operation and maintenance standpoint. And as I mentioned, it utilizes the full benefit of IEC 61850 standard. So again, here is a little more detailed view of what protection packages can be loaded on SSC 600. It again comes with the base protection functionality, and on top of that, we can add power transformer protection, machine protection, power quality measurements, feeder or line protection, including a distance protection, and interconnection protection for DER, distributed energy resources, tap change of control, and bus power protection. For bus power protection, we have option of arc flash detection within the switchgear, and also the low impedance based bus bar differential protection. So all that can be achieved using SSC 600. Okay, now in the next available minutes, we'd like to show you some application examples. Example one is a typical one line with a transformer, bus, feeder, motor, line differential, and generator protection. Okay, and example two, we are going to look at one line with a double-ended substation with a main type of arrangement with feeder, line differential, and a small motor, and an automatic bus transfer scheme. Okay, so here is one line for the example one, showing all zones of protection, so which we discussed earlier. So we have a main incomer and then outgoing feeders here. So what we have shown here is with the traditional CT and the PT here. So the main relay has a transformer differential protection as well, because it has a transformer with a breaker on the high side and the low side. And so the CTs are connected from both sides. And of course, there is a line PT and the bus PT also wired into the relay. And the respective feeders will have its own protection. For example, here is a small motor, 500 HP motor. It has we can choose an REM 615 configuration B for protecting that that motor. And for a larger motor which needs a differential protection, for example, can have an REM 615 configuration E. And here, this is a long feeder. The third one is a long feeder, which needs the basic 50-51 protection, and also needs a line differential protection. For that case, we can use an RED 615, D for differential, RED for differential 615, and this is a configuration D relay applied for this feeder. It's a long feeder. And then we have the next feeder, we have an overhead line. We can use a regular feeder relay called as REF 615, and again, configuration N. So that is a relay which we can choose for this application. And here, the last one is a generator feeder, which is again connected to the bus bar here. So for generator, we use REG 615 configuration D. So it has its own CT, and it has its own PT input. And of course, it has a differential. It's a large generator, so we need a differential protection for that. So CTs are connected to the relay from both the bus side and the neutral side of the generator. Okay, so now we will look at how we digitize it. As we digitize it, what are the changes we need to make in this traditional one line? Okay, I need to mention one more thing here. Here, I missed one relay. So this device here is REF 615, but this is used for bus differential, the traditional high impedance bus differential scheme, which many of us are familiar. So traditional high impedance bus differential scheme requires its own set of CTs. So as you can see here, a dedicated set of CTs are used to develop this scheme. Okay, so the CTs are summated from the main and outgoing feeders, and then it is connected to the bus bar differential protection relay. In this case, it is RDF 615 configuration N. Okay. Now, with the 61850, we can adopt a cost-effective bus protection, thus eliminating a dedicated bus protection relay, as you can see here. So we can utilize the current information from the main, the generator, and the other outgoing feeders, and then we can create a bus protection scheme logic within the device here at the incomer relay, which will look for the current flow into the bus and out of the bus. And thus we can achieve a very selective protection for bus protection application with the same devices what we have, without having any additional set of CTs or an additional set of relay, as we have seen in the earlier case. So with this arrangement, we can have a very fast bus protection scheme without having additional hardware. So this adds to the cost efficiency of the switchgear. Now, when we talk about the sensor, we're now looking at how we can convert the traditional CT and the PT to current and voltage sensor. So the feeders can be changed to current and voltage sensor in this case. So here we have the feeder relay. We have replaced the CT with a current sensor, okay? And then the PT with the voltage divider here, the voltage sensor. So this relay operates based on that. For ground fault application, we would still need a ground CT, because it's as you see, the ground CT or the donut CT is encompassing all the three phases. So there is no sensor technology for a ground or equivalent to a donut CT at the moment. So if there is a requirement to measure the ground CT directly, we need to use a donut CT. But the other way of doing a ground protection is using a calculated I0 based on the phase current. So if we have the three-phase currents coming from the current sensor, and we can utilize that the current voltage, the current of the phases to calculate the I0 and use it for ground protection. So that is other way of doing it. then we can think of changing the small motor to current sensor. So here's a small motor feeder. We can change the CTs, replace that with a current sensor for a motor feeder, and then achieve the same motor protection which we had before. And in this case, the relay is going to be REM 615 configuration D. And as you have noted, for the feeder, the configuration is changed to configuration L, because that is the configuration which accepts a current and voltage sensor input. So we change the configuration of the relay depending on the type of analog input it receives. Okay. And now we can now remove the voltage connection to the motor relay with the current sensor input. So earlier we had wired the voltage, the PT into this relay as well. Now with this relay in place, we can remove that wiring to the PT bus PT to this relay, and then as a next step, we can also use a differential relay using current sensor. So you have we have a differential relay RED 615 configuration E, which works on current sensors. So we can use a current sensor to as an input for this relay, and then we can achieve the current differential protection. And as a next step, voltage connection can be removed from there, from the bus PT for the differential relay, line differential relay also. And instead of that, we can use the IEC 61859-2LE sample values by which this relay, this feeder relay, which has a voltage sensor input wired to this relay, that relay can share the voltage signals over sample values to the other relays. So we eliminate that wiring. Okay, so that was an example with an REF 615 series relays, but there is another way of doing a digitization using REX 640. So with the REX 640 relay, we have a differential protection possibility for for the large motors, the transformers, and the generators as well. So as you can see here, if you note here, REX 640, the relay which we discussed earlier, takes the CT input from the high side and sensor input from the lower side. So that is another flexibility we have in 640 relay. So you can have one set of from one side of traditional CT, and the other side a sensor input, which typically comes from the medium voltage switchgear, and then you can achieve the differential protection based of that. Okay, so that is possible. And then the voltage inputs are taken from the voltage sensors. And same is the case here with the large motor. We can have from the bus side, we have the current sensors. From the neutral side of the motor, we have the traditional CT coming, and when we have we can still achieve the 87M, which is a machine protection or differential protection for motor using those inputs. Okay, the same thing we can do for generator protection. So the generator has an REX 640 relay also with a similar arrangement. Phase side has a current sensor, and the neutral side has a traditional CT. And of course, the voltage comes from the voltage sensor. So with this, all the standard protection can be achieved, the differential protection can be achieved, and in addition, we have now the ability to share the voltage between the devices. So which means the bus voltage can be shared between all the devices, and if there is a line voltage to be checked for synchronizing purpose, so that can be checked as well. For example, here in the generator protection, you have a line PT or the line sensor, voltage sensor, and then the bus voltage sensor coming from the sample value, and it checks the synchronizing condition before you can close this breaker and bring the generator onto the bus. So additionally, to minimize the inventory, and increase the flexibility. All feeders can be converted to an REX 640. And it can be used for all applications because REX 640 is very flexible and with respect to hardware modularity as well as the software modularity. So the same hardware can be used, and then different protection application can be loaded based on the requirement of each of those feeders. The another possibility is by using an SSE 600. SSE 600, as we said earlier, it's a smart substation control, or is a centralized protection where you can have all the protections in one place. So you can have the transformer, the small motor, the feeder, and the bus protection in the device. And in this case, you can see here for the mains, we are showing SMU 615. SMU 615 is a dedicated merging unit. If you don't want to use a relay, SMU 615 can publish the current and voltage signals out into the process bus, and then that signal is subscribed into the SSE 600 to do the protection. For example, for the transformer and the main incomer here. And for the feeders, you can have dedicated. You can have either a SMU 615, which is a substation merging unit, or a relay, like an REX 640 in this case, or an REF 615. So the requirement is that the REF 615 or an REX 640 can also publish, as I mentioned earlier, the sample values. So it acts as a local protection, and also it acts as a merging unit, which can publish the sample values. And so with an SSE 600, you can have a main protection at SSE 600 level and backup protection at the local level with its own respective IED. Now going to the example 2. This is another one line, which is a main tie main arrangement. So each main has its own relay, and the tiebreaker has its own relay. And this is a scheme with the standard CTs and PTs, but utilizing goose messages. So you can still utilize goose messaging even with the traditional CT and the PTs. So in this case, we would use an REF 615 configuration N for the main application, because it needs a sync check protection as well. So we have the ability to do that in configuration N, which brings in the CT from the line side and the PT as the line PT, and also it can take the bus PT voltage. And the same is the case with the main too. And in the case of tiebreaker, again, we need a sync check functionality here. And we have a version called as REF 615 configuration P, which can be used for tiebreaker application. It has 25 at the same time other standard protection. So it has input from both voltages, both from bus A and the bus B. And for feeder application, we can use a configuration B or a configuration F, depending on the case. So here, I'm sorry, this is a motor relay. So the motor relay is an REM 615 configuration D, and here is an RED 615 configuration D with the traditional CT and the PT input. And here is an REF relay because it's an overhead feeder with the configuration F. It has 50, 51, 50 breaker failure, 67 directional protection, arc flash detection, and so on. And again, here is the same feeder, same type of feeder. So one of the things which we can do here is achieving an automatic transfer scheme. Traditionally, when we have digital relays or other type of relays without having communication capability or logic building capability, people use a separate device called as an ATS, and it's a logic controller and so on to achieve an automatic transfer scheme. But with the Reliant relays, we have the ability to achieve an automatic transfer scheme, the bus transfer scheme, just with the relay and relays itself. So we don't need any additional hardware to achieve the ATS. So logics can be built between the main one and the main two and the tiebreaker, and they can talk to each other and check the voltage status, availability of voltage, and so on, the breaker status, and then do the bus transfer, whether it's offline transfer or an online transfer. That can be decided based on the application, and then we can achieve a very cost-effective automatic transfer scheme just with the relay and relays itself. Okay, here is the same one line with the current and voltage sensor instead of the traditional CT and the PT. So replace the CT and the PT with the sensor, but then we need to choose the respective type of relay which can accept that relay. So that's only change here. So we changed the relay configuration to REF615 configuration L for the main one and main two, and also for the tiebreaker. So it's an REF615 configuration L. The REM is an configuration D, which accepts the sensor input, and line differential is configuration E, RED615, and for the feeder is we use the same relay, REF615 configuration L. So the protection functions can be enabled based on the requirement for each feeder. As you can see here, even though it's the same relay, configuration L, we can use the different protection functions here for this feeder because it requires additional functions because it's a tiebreaker, whereas the feeder relay may not require all the functions used in the tiebreaker. So we can disable all those or totally delete those. So there is a great amount of flexibility in how things can be tied together and programmed in relay and relays. Okay, so in summary, why digital switchgear? It reduces copper wiring by using Ethernet communication and using goose messages. Further, it reduces copper wiring, taking advantage of sample value sharing based on IEC 61850-9-2 LE standard, and we can design reliable communication networking to make sure that no information is lost at any point in time, and we can go full digital using the current and voltage sensor instead of traditional CT and PT. Number two, we can select the protection required for each specific application, whether it's a feeder, transformer, small motor, or large motor, line differential, or generator. We have several different IEDs and applications to choose from, and we also can do redundant protection using SSE 600. And we also looked at some of the very cost-effective schemes which can be built based on this technology, like cost-effective auto transfer scheme, cost-effective bus protection, and cost-effective redundant protection. And that brings to the end of my presentation. Thank you.